Howdy, friends. Hope you've all been doing well. You might have noticed that during the intro, the game scene now supports text and 2D sprites. That's because I've been busy adding support for both 2D and 3D objects. Up until now, adding something to the game scene involved writing code, which is generally how these things work in programming. However, that's not the best look for a game engine. Usually, you would interact with something called a graphics user interface, or GUI, using your mouse and keyboard. This early on, I decided to go with a very simple approach. I do have plans to revisit this, but for now, let's just cross that can when we kick it. Already off to a great start. GUI itself is rendered using an orthographic projection, which is a way of projecting 3D objects onto a 2D plane. Knowing this, we can use screen coordinates to position our GUI elements. Then it's just a matter of finding the bounds of said element relative to its position, and calculating whether or not the mouse's position lies inside of those bounds, as the mouse also uses screen coordinates. Calculating the bounds is also simple. We just need to know the min and max vertices of our object's mesh. Funny enough, an issue I ran into early on was that my quads are always rendering as a single pixel. Turns out it's because the position vertices I was using were in world space. But that's a simple enough fix. Since we'll be setting the width and height of our GUI elements anyway, we can just calculate the vertex positions and the bounds of our vertex in the same step. Let's say we want to position our element in the center of the screen. We can also give it a width of 150, and let's make the height 100, just to match the 3:2 aspect ratio of our window. With the screen space origin point in the top left, the position at the center of our screen is just half the width and height of our window. We can also use this approach to calculate our vertex positions. For the top left corner, we just take half the width and height of our element and subtract them from its origin. For the bottom right corner, we do the same thing, just adding instead of subtracting. As far as quads go, that's our min and max taken care of. For the other two vertices, we follow pretty much the same steps. Top right vertex is just the width added to the x component of the min. Bottom left, we just add the height to the y component of the min, or subtract the width from the x component of the max, or add half the height to the origin while subtracting. You get the point. With all that taken care of, we can finally make use of the mouse input callbacks provided by the lightweight Java game library. You can do this to update the button's color or text when we hover over it, as well as fire off events when we click. This will be very useful for the next challenge of instance rendering. I did mention this briefly in my last video and even plan on making this video all about instance rendering, but while looking for thumbnail ideas, I actually stumbled across another video that explains instance rendering better than I could. That's not me being humble, by the way. I actually recorded an entire video going into great detail on the mechanics behind instancing, and the entire time it felt like I was second guessing myself, scrolling through the Chronos documentation to make sure I didn't leave anything out, and repeating the words vertex attribute array past the point of semantic satiation. Instead, I want to cover my solution, since my goal wasn't to just add instance rendering, but to do so with a more object-oriented approach.
Oh my god, bro.
Oh, hell no, man. What the fuck?
Brief rundown. A vertex buffer object, or VBO, is an array of unmanaged memory sitting on the GPU. So once we've placed our data into a VBO, we'll need to describe its composition to our graphics card so that it knows how to interpret it in our shader. In short, a vertex attribute array can be seen as our description, telling the GPU the size of each vertex, its placement in the array, and its location in the shader. Now, my initial implementation only had support for two types of buffered arrays, ones with a single attribute or ones with multiple attributes. For context, a single buffer could hold vertex data for positions or multiple attributes, including positions, colors, and texture coordinates. This worked for most types of data, including instance data, but what I hadn't accounted for was matrices. The maximum vertex size allowable for a single location is 4, but a 4x4 matrix, as the name implies, takes up 4 locations in a shader. This basically meant I had to refactor my implementation from the ground up. I needed a way to track vertex attribute arrays where the same attribute could be spread across multiple locations in the shader. These would also have to be sequential, since I can't just have a matrix sitting at location 3 with another vertex attribute sitting at location 4. We also have to reserve the next 3 locations that come after it. In the end, this meant splitting my original vertex attribute array class into 2 separate classes. The first would contain variables that apply to every vertex in the array, like stride and primitive type. The second class would contain vertex-specific data, like its attribute name, size, location, and offset. The primary unique identifier would be the location, as every vertex, even ones with the same attributes spanning multiple locations, need to have a unique location, so the graphics card knows where to pass it into the shader. So now, my game engine supports single attribute vertex buffers, which are my personal favorite, and it also supports multiple attributes, so we can have our position at offset 0 with the size of 3, followed by normals with an offset of 3 and a size of 4, and so on. But now, and most importantly of all, it supports multiple instances, for lack of a better term, of the same attribute. So for instance, an instance matrices attribute appearing 4 times, all with the size of 4, a divisor of 1 so that they each get applied per instance rather than per vertex, and offsets of 4. Oh, by the way, I should mention, both the stride and offset need to be in bytes. So technically the offset separation is 16, and the stride is 64. But it's not like that took me a whole day to figure out or anything. Anyway, I think I'll go touch some grass. Speaking of, I'm looking forward to adding trees to my scene using instance rendering. I'm honestly not even sure how many instances my laptop can handle at this point. Maybe 6. I don't know. Don't forget to, relax your shoulders, unclench your jaw, drink plenty of water, that sort of thing. Okay, bye.